Hello everyone. In this video we are going to solve one equation with two unknowns. But since this equation uses complex numbers, then it can be dissected into two equations with two unknowns, which allows us to find the solutions if there is any. This is the equation. 2.5 at the phase of theta 1 plus 3 at the phase of theta 2 equals 1. It is basically two complex numbers in polar form. They have known magnitudes but unknown phases or arguments, and when added together, they should give us the number 1. Since we have a summation, we proceed by transforming the polar numbers to their rectangular form. This is done as the magnitude r times the summation of cosine the phase and j sine the phase, where j is the unit imaginary number, square root of -1. We apply this transformation to both complex numbers in the equation and simplify to get a new version of the equation in rectangular form. For this equation to be true, the real parts in both sides of the equation should be equal, which gives us equation number 1. And imaginary parts of both sides of the equation should also be equal, which gives us equation number 2. Now we have two nonlinear equations with two unknowns. We can find solutions using mathematical packages or some numerical and graphical techniques. But here we are going to solve them analytically. When solving analytically, the trick is how to isolate the unknowns and become able to write one of them in terms of the other. This is what we are going to do. By squaring equation number 1, we'll get two terms of cosine squared and one term of the product of the cosines. And by squaring equation number 2, we get two terms of sine squared and one term of the product of the sines. Now by adding both squared equations, we'll produce couple terms containing cosine squared of the angle added to the sine squared of the same angle, which is 1 according to the very well-known identity. There is also the term cosine theta 1 cosine theta 2 plus sine theta 1 sine theta 2, which is actually the identity for cosine of the angle difference, cosine theta 1 minus theta 2. With this, the relation between theta 1 and theta 2 can be found after applying the inverse of the cosine to obtain two possible solutions. Theta 2 equals theta 1 minus 161.8 degrees, and theta 2 equals theta 1 plus 161.8 degrees. Now the problem becomes more straightforward. We substitute each of these relations in one of the original equations so that we have one equation with one unknown. We first pick theta 2 and substitute it with theta 1 minus 161.8 degrees in equation number 2, which is the simpler equation. We use the identity for sine of the angle difference to have the terms of sine theta 1 and cosine theta 1 only. Then we solve the equation by dividing by cosine theta 1 to end up with tan theta 1 equals minus 2.677. We take the inverse of the tangent and obtain two possible solutions for theta 1, minus 69.5 degrees and 110.5 degrees. Substituting for theta 2, we will get minus 231.3 degrees and minus 51.3 degrees. So now we have two pairs of solutions, or let's say possible solutions. But we are not done yet. We have to do this again for the other relation, theta 2 equals theta 1 plus 161.8 degrees. We follow very similar procedure as the first one and obtain another two pairs of possible solutions, theta 1 equals 69.5 degrees, with theta 2 equals 231.3 degrees. And the other pair is theta 1 equals minus 110.5 degrees, with theta 2 equals 51.3 degrees. And now we have a total number of 4 pairs of possible solutions that we must test by simply plugging them in the original complex equation. 2.5 at the phase of theta 1 plus 3 at the phase of theta 2. By doing so, we got minus 1 2 times and plus 1 2 times. But the right-hand side of the original equation is plus 1. So 2 of those pairs failed the check, and the other 2 pairs passed the check, which makes them the only solutions of the equation. A visual demonstration of these solutions is possible by looking into the solutions on complex plane. Let's apply the first solution. We have a vector of magnitude 2.5 and phase of 110.5 degrees. We also have another vector of magnitude 3 and phase angle of minus 51.3 degrees. When adding these two vectors together, we basically attach head to tail and measure from the first tail to the second head. What we get is a vector of magnitude 1 that aligns with the positive x-axis, which makes the phase 0. This is indeed the right-hand side of the equation. You can also visualize the other solution in the same way, but with the vectors mirrored in the bottom half. That's all for this video. I hope you liked the content and learned with joy. Thank you for watching, stay safe, and see you in the next video.